All right, good morning. Welcome back. I hope you're doing well, staying safe. I hope you had a great weekend and hope you're ready to roll for another week of awesome chemistry class. I'm looking for a few people today. I'm looking for Alex, looking for Joseph, Santino, and Nidal. If you're here, please let me know. So again, Alex, Joseph, Santino, and Nidal. If you're here, please let me know. All right, let's check out the COVID report for today, see where we stand as a county, see the numbers. Right now in the county, there's 460 active cases of COVID in the county, 20,238 resolved cases of COVID in the county. Numbers increasing. Resolved. Number of deaths in the county, there are 414. So over the weekend, we added one more death to the toll. Hospitalization numbers, there's 18 people in the hospital and one person in ICU. The vaccine numbers are quickly increasing. Good sign right there. Let's check out the daily positive numbers of COVID in the county. Here's a curve from day one till a couple days ago. Zoomed out version of the curve, you can see what's going on. The last few days worth of data, we've been relatively steady at like a higher mark because it's been a little bit higher for the last few days. So there's probably an average for that data. Probably the week before, a little bit lower of an average. And then maybe the month before, the week before, you can see it's a little bit higher again. So I'm not really sure what happened on this week, but it's definitely lower than last week. But let's see what those numbers actually are. Let's see what they read. The 17th, we had 39 cases. 16th, there was 49 cases. The 15th, there's 29, 49, 45, 50. Then two lower days as well. So you can see there, we're closer to the 50 mark than what we've been. So maybe our average is increasing slightly over that last week of data. But it's not too crazy. You check out the data again from a zoomed out version, it's not like 100. It's not, hopefully we don't get the 100 again. Hopefully we don't get this number of 364 on January 1st again. But just know it's definitely still out there, still in the community. Be smart, be safe, take care of yourself, take care of your loved ones, wear your mask correctly, sanitize, sanitize, sanitize. There's a song about that. A little crazy, but sanitize, sanitize, sanitize. All right, there's a COVID report for today. Let's figure out what's going on for the best class of the day. See what's happening in chemistry. Welcome back. Quote of the week comes from an unknown source. Good things come to those who wait, but better things come from those who work for it. So if you're willing to work in this class, you'll be successful. You'll have good things. You'll have good results. You'll have good grades. That quote, definitely true in life. You're willing to work for anything, you'll have good things. You get a boo in life. You're willing to work for that relationship, then good things will come out of that relationship. You get a job. You're willing to put the extra effort out and work a little harder, then good things will result in that too. College. Go to college. You're willing to work hard in college. You'll have that degree. Hopefully a good job will come out of that as well. I like that quote. Today's Monday, April 19th, 2021. Today's day 2. We're going to get closer to wrapping up unit number 8, oxidation and reduction. We will definitely finish up Voltaic cells today. So we'll put a wrap on Voltaic cells, topic 4 today. Before we do that, we're going to watch a flick on how batteries work. We'll review Voltaic cells. We'll take a look at our example in the guided notes for Voltaic cells. We'll analyze some examples on Voltaic cells on topic 4, and then we'll give you some time to work on the exit paths for Voltaic cells too. That's our goal for today. It's a relatively light day for class. I'm not going to hammer you too hard with notes today, but we'll analyze several examples for today's class. So Voltaic cells, when we start off the unit, I showed you a battery under an elmo. I'm like, how does this battery work? It's actually the same battery. How does a battery work? And then there's a positive charge, there's a negative charge. A lot of you guys told me about maybe the charges. Maybe you said something about electrons. But by now, you should know a lot more information on how a battery works. How does a battery work? Let's review for a second. So starting off, I'm going to make my little drawing of a voltaic cell. Let's start fresh. Think about that demonstration that I did for voltaic cells. Voltaic cells, what do? We start off with a couple beakers. I took beaker 1. I took beaker number 2. So here we go, drawing class with Mr. Brown again. Digital drawing with Mr. Brown again. There's beaker 1. There's beaker number 2. The next thing you note is I made an electrolytic solution. I made an electrolyte. So after I did that, I took water, I took salt, I mixed them both together, made a saturated solution of salt water. I poured them into each beaker. Think about what I did for that demonstration. Next thing I did is I labeled electrodes. And I said, hey, there's copper, zinc, magnesium, and lead electrodes. I put one electrode in one beaker, copper, and I put the second electrode in another beaker. Those are electrodes. The next thing I did is I took a paper towel, I folded it in half a few times, and then I put the paper towel in both solutions. This was my salt bridge. So the salt bridge connects both beakers, and in the salt bridge, it allows ions to flow. So salt bridge, that paper towel, I saturated the paper towel by using a pipette, putting the electrolytes on there. There's my paper towel that connects both beakers. What else did I have? I took a copper wire or alligator clips. I connected the electrode to a voltmeter, and then connected the other wire to the electrode. So again, I took the electrodes, connected it to the voltmeter, and this gave us a reading. It gave us a potential difference or a voltage. These are the major parts of a voltaic cell. Hopefully you could draw one of these. Hopefully you could describe it. Hopefully you know the functions of everything within this voltaic cell. Let's ask some questions here. Question number 1. What is the purpose of the salt bridge? Purpose of the salt bridge. Please put in the chat, what's the function, what's the purpose of the salt bridge? Hi, Alex. Please try to get here a few minutes earlier. Please put in the chat, what's the function of the salt bridge? What's the purpose of the salt bridge? Why is there a salt bridge there? Salt bridge is that paper towel. Yes, that's good, Tristan. Yes, Jumila. For what? What's the purpose of a salt bridge? Anybody know? Not electrons, but close. Some. Yes. Ions. Perfect. Perfect. Thank you very much. Yes, Jumila, you're right as well. Answers to keep a balance. Yes, that's the purpose of a salt bridge. Maintain balance. Provide a path of flow, someone said. Allow free flow. Yeah. And then someone corrected their answer. Provides a path of flow of ions. The salt bridge allows ions to flow back and forth between both chambers. What are ions? They're going to be positive and negative charges. So these positive and negative charges are going to bounce off from each beaker to find that balance. to keep it balanced. Good. So again, that's just going to be a porous membrane that allows ions to flow through it. If that ever dries up, then the battery's not going to work anymore. So number one, first question, purpose of a salt bridge, you could have just said, allow ions to flow. Allows ions to flow. Next question. Where do electrons travel? Or how do they travel? In this Voltaic cell, how do electrons travel? Or where do they travel? Please record your answer in the chat. Think about it. Where or how do the electrons travel in a Voltaic cell? Yes, John. Thank you. Several answers you can give me for this one. How do electrons travel? Where do they travel? In a Voltaic cell. Not sure about that second response. Someone said through the wires. They definitely flow through the wires, the copper wires, the red wires that are in the diagram. Nice. They flow through the wires, and someone said they flow to the cathode. Yes, electrons flow from anode to the cathode. Electrons travel through the wires from anode to the cathode. So yes, they're definitely going to flow through this wire up here, one way or another. So electrons flow through the copper wire. They flow from the electrodes, anode to cathode. Next question for you guys. What's the purpose of electrolytes? Why do we have electrolytes there? Why didn't I just use distilled water or just water? What is the purpose of electrolytes? Why did I use an electrolytic solution? Uh-oh, tough one. Why do I use electrolytic solution? To allow electricity to flow through it. If I did not put the table salt in there, electricity would not have the ability to flow or be generated. There has to be an electrolytic solution. What's an electrolyte? It's an ionic compound dissolved in water, or it could be an acid or a base. So without the electrolytic solution, Gatorade, salt water, whatever, this would not happen. You need electrolytes in this situation. Last question on Voltaic cells. What type of energy is created? What type of energy is created in a Voltaic cell? One for one. Two for two. Thanks, Irvin. Thanks, Alex. What kind of energy is made in a Voltaic cell? Thanks, Asim. Yeah, so it's going to make electrical energy. Electrical energy is made. Electrical energy is created. I started thinking I have two more questions now. What's the conversion of energy? What is the conversion of energy? in a voltaic cell? What is the conversion of energy in a voltaic cell? How is energy converted in a voltaic cell? From what to what? What is the energy conversion in a voltaic cell? You told me it's creating electrical energy. So it's making electrical energy. What's making electrical energy? It's going from, oh, thank you. It's going from what to what? Yes, Irvin. Thank you. Energy conversion of voltaic cell goes from chemical energy to electrical. It is making electrical energy. Inside this battery right here, you have chemicals reacting to make electrical energy. So you could charge something, you use a toy. That is the energy conversion. Last thing about voltaic cells, is it spontaneous or non-spontaneous? Spontaneous. Which one is it? Spontaneous or non-spontaneous? Voltaic cells, are they spontaneous or non-spontaneous? Voltaic cells are spontaneous chemical reactions, redox reactions. What else should you be aware of for a voltaic cell? What else should you know? You should know that a voltaic cell has two different chambers. You should know it's going to have a salt bridge. You should know the conversion of energy. You should know red cat and an ox, that phrase. You should also know the phrase about Leo. Leo says grr. We should know electrons flow from anode to cathode. Those are the basic concepts you should be aware of. Hi, Nidal. Please try to get here a few minutes earlier, but welcome. So that is a voltaic cell. That is a battery. Does anybody have any questions on anything we did there? Please ask if you do. Any questions? Again, you should understand what this diagram is. You should understand the questions or the concepts behind the voltaic cell too. Any questions? Maybe you drew this for grandma over the weekend and grandma had a question for you. They didn't know the answer. I'm guessing you knew the answers, but do you have any questions for me? All right, you now know how a battery works. You know how a car battery works. You know the basic idea of how your computer battery works. You know how your phone battery works. A little bit more. Here we go. How does a battery work? Enjoy this video.
You probably know the feeling. Your phone utters its final plaintive bleep and cuts out in the middle of your call. In that moment, you may feel more like throwing your battery across the room than singing its praises. But batteries are a triumph of science. They allow smartphones and other technologies to exist without anchoring us to an infernal tangle of power cables. Yet even the best batteries will diminish daily, slowly losing capacity until they finally die. So why does this happen? And how do our batteries even store so much charge in the first place? It all started in the 1780s with two Italian scientists, Luigi Galvani and Alessandro Volta, and a frog. Legend has it that as Galvani was studying a frog's leg, he brushed a metal instrument up against one of its nerves, making the leg muscles jerk. Galvani called this animal electricity, believing that a type of electricity was stored in the very stuff of life. But Volta disagreed, arguing that it was the metal itself that made the leg twitch. The debate was eventually settled with Volta's groundbreaking experiment. He tested his idea with a stack of alternating layers of zinc and copper separated by paper or cloth soaked in a saltwater solution. What happened in Volta's cell is something chemists now call oxidation and reduction. The zinc oxidizes, which means it loses electrons, which are in turn gained by the ions in the water in a process called reduction, producing hydrogen gas. Volta would have been shocked to learn that last bit. He thought the reaction was happening in the copper, rather than the solution. Nonetheless, we honor Volta's discovery today by naming our standard unit of electric potential the volt. This oxidation-reduction cycle creates a flow of electrons between two substances, and if you hook a light bulb or vacuum cleaner up between the two, you'll give it power. Since the 1700s, scientists have improved on Volta's design. They've replaced the chemical solution with dry cells filled with chemical paste. But the principle is the same. A metal oxidizes, sending electrons to do some work before they are regained by a substance being reduced. But any battery has a finite supply of metal, and once most of it has oxidized, the battery dies. So rechargeable batteries give us a temporary solution to this problem by making the oxidation-reduction process reversible. Electrons can flow back in the opposite direction with the application of electricity. Plugging in a charger draws the electricity from a wall outlet that drives the reaction to regenerate the metal, making more electrons available for oxidation the next time you need them. But even rechargeable batteries don't last forever. Over time, the repetition of this process causes imperfections and irregularities in the metal's surface that prevent it from oxidizing properly. The electrons are no longer available to flow through a circuit, and the battery dies. Some everyday rechargeable batteries will die after only hundreds of discharge-recharge cycles, while newer advanced batteries can survive and function for thousands. Batteries of the future may be light, thin sheets that operate on the principles of quantum physics and last for hundreds of thousands of charge cycles. But until scientists find a way to take advantage of motion to recharge your cell battery, like cars do, or fit solar panels somewhere on your device, plugging your charger into the wall, rather than expending one battery to charge another, is your best bet to forestall that fatal bleep.
All right, there's your battery. You should know a lot about the battery at this point. Okay, please open up your guided notes. Let's see where you left off in class with Voltaic cells before the weekend. And let's see how we did with that Voltaic cell example. So here we go. Unit 8, oxidation reduction. There's a Voltaic cell to the right for the diagram. The one all the way to the right, it's actually topic number 5. That's an electrolytic cell. So we talked about assigning oxidation numbers, done. Talked about redox reactions, done. Talked about half reactions, done. Voltaic cells will be done at the end of today's class as well. We only have one more topic to discuss. It's topic number 5, electrolytic cells. And that probably will be done next class. We'll probably finish that whole topic next class. I'm not going to scroll through this stuff right now because we already have it in our notes. And I just want to get to Voltaic cells today. So topic 4, Voltaic cells. We talked about oxidize and reduce. It's a redox reaction. It's an electrochemical cell with a flow of electrons. We talked about Voltaic cells. Spontaneously react. They have a flow of electrons. And then we talked about an example with this spontaneous reaction. We analyzed this redox reaction. We figured out the partial half reaction. Then we figured out the reduction and oxidation half reactions that we did last time. And from that, we made a Voltaic cell. We drew a diagram of a Voltaic cell. We labeled it with anode. We labeled it with cathode. Leo says GER. We labeled the electrodes, all that stuff. We talked about a salt bridge. We talked about electron transfer. We talked about the cathode and anode, identifying the anode and cathode. We looked at table J for activity series. And then we talked about this phrase, red cat in an ox. We know that phrase. You should know that phrase. Reduction at the cathode and anox, the anode's the site of oxidation. Should be aware of that. And then at end of class, I said, hey, let's go through, let's figure out all this information on this example. Let's see if you guys could do this as well. So I gave you like 20 minutes to go through and try this out. Hopefully you went through and attempted it. It looks like I did here. But I want to do it again with you, just to make sure we're all good to go so we can move on forward. So again, you had to figure out all this information about this redox reaction. This should be completed by you already. Let's see how you did. It says, from the formula above, determine each of the following. What's being oxidized, reduced, the half reactions, the anode, the cathode, the drawing of the Voltaic cell, and the flow of electrons. The first things first, you had to assign the oxidation numbers for everything in the chemical reaction. PB's, it's an atom, its charge is 0. Cu was given to you with +2, PB was given to you with +2, Cu's charge is 0. So the first thing I did was represent a half reaction, partial half reaction. PB0 goes from PB0 to PB +2. You don't have to put the phases in here. I will just represent them. So aqueous. The next one goes from Cu +2. Next partial half reaction. Cu +2. Aqueous. 2 Cu0. Solid. So that is a partial half reaction. You're representing both equations from the reactant to the product. You're representing each element from the reactant to the product. Now I would suggest figuring out what's going on for each element. PB is going from PB0 to PB +2. I would say, hey, what's going on from PB0 to PB +2? You're saying, oh, it's going from an atom, 0 charge, protons and electrons cancel out, to PB +2. And you're saying at home, oh, Mr. Brown, the charge from 0 to +2 is increasing. That charge is increasing. And then you're thinking about in terms of electrons, what's going on there? Its charge is increasing. Is it going to gain or is it going to lose electrons? And then you're saying, oh, it's positive, so you have to take an electron, throw it away. Take another one, throw it away. In terms of electrons, PB is going to lose electrons, Leo. So the next thing I would do is put my little phrase Leo right there. If that's losing electrons, this copper below is going to have to gain electrons. Gaining electrons reduction. It is. It's going from +2 to 0. Think about that process. +2 to 0. The charge is getting smaller. The charge is getting reduced. It's reduced its oxidation number. Therefore, it's going to be reduction. Grr. That helps us out quite a bit. Must know what's being oxidized, what's being reduced. Oxidized, Leo. What's being oxidized, PB0. I'll paste it there. What's being reduced, it's going to be the copper. Oxidation half reaction, pretty easy now. We have the partial half reaction. This is oxidation partial half reaction. This is going to be my oxidation half reaction. Need some help here. Where do my electrons go for oxidation for half reactions? Reactant or product side? Oxidation, half reaction, where do the electrons go? Question for you, where do my electrons go for oxidation, half reaction? Need some help here, guys. Product side, good. Product side of the equation, or to the right, thank you. So it's gonna be the product side. How many electrons? Someone in class help me out. 2 electrons, perfect. 2 electrons to the right. That has to obey the law of conservation of charges. We lost 2 electrons. It has to balance out on both sides. So since 2 electrons are lost, you have to balance it out with however many were lost. Reduction half reaction. It's going to be this partial reaction. And we should know that reduction half reaction, the electrons are on the reactant side. So the reactant side, you have plus 2 electrons. Anybody have any questions on what you did there? So hopefully you got those answers. We should have gotten those answers from topic number 3. So we talked about this in topic number 3, half reactions. All this stuff we did right there, you should have done already. Should have been able to do before voltaic cells. Which one's my anode? Please put in the chat. Which one's my anode? Lead or copper? Please throw in the chat. Which one's the anode? I have 24 people on and wait for at least 5 responses. Which one's the anode? Lead or copper? Thank you. Three for 3, thank you. 2 more responses. Which one's the anode? What'd you put there? Gave you a lot of time to do it last time. Four for 4, 1 more response. We could go through it just to check your work. Thank you guys, appreciate it. All right, so a lot of people said lead. Everybody said lead that responded. Only have 5 responses. If you didn't respond, I'm guessing you're not really sure about it, but let's just check it out. So lead, a lot of people said. Let's see if that's correct. So we have 2 different metals here in the situation. We have lead, we have copper. There's a couple different ways to label your anode and cathode. The first way I'm going to tell you or teach you, revisit how to do, is look at table J. Check out table J in the reference table. It's page number 5. Find the 2 metals. We have lead, we have copper. Again, table J says activity series, says most active on top, least active on the bottom. Locate the 2 metals. We have lead, Pb, and copper. There's Pb, and copper is below. When we look at this table, I told you think about this table as the alphabet. Alphabet starts with A. A is at the top. A, B, C, D, so on and so forth. Z will be all the way down here. So the alphabet starts with A all the way to Z. The A is at the top. The A is going to represent the anode. The C is lower. This is your cathode. Notice that A, anode, is above cathode. Once you find your 2 metals, the one on top is going to be the anode. The one below is going to be the cathode. So if you look at this right here, you can figure out, oh yeah, Pb is definitely my anode. Cu is going to be my cathode. A is above C. In the alphabet, here, anode above cathode. That's an easy way to figure out anode and cathode. So again, Pb is my anode. And cathode is going to be Cu. So lead, anode. And all this is just checking your work here. Cathode is going to be Cu. Drawing of the voltaic cell. So I told you guys you could copy and paste the old diagram that we already did instead of recreating it, or you could draw it again. Totally up to you. And the flow of the electrons comes from that diagram too. So here we go. Let's take that diagram again. Let's copy and paste it. It's going to be very similar. Taking this diagram, I'm going to click on it, blue box around it, hit copy, Control C. I'm going to scroll on down to the box, paste it right in there, Control V. Looks like I already pasted it in. Let's paste it again. Make this a little bit smaller so it fits within the cell. And then I told you, you could just just edit this a little bit, switch it out, the appropriate things. Okay, so that's a diagram. The first thing I would do is edit my formula, the chemical reaction. This is not correct. It's not zinc and copper, it's lead and copper. So take the chemical formula, copy, Control C, and paste it below. So paste it. I'm going to get into my drawing board. I'm going to get rid of this formula. I'm going to change it up. I'm going to paste that formula in. I want this voltaic cell to represent this formula. All right, we said PB to Cu. These electrodes, one electrode is going to be PB, one's going to be Cu. I'm going to leave copper alone. Leave it the way it is. So I have to edit that one. Let's change the left electrode to lead. So this is PB electrode. This is going to be lead, solid. Let's see if the rest of this makes sense. You told me that lead was my anode. Yes. If lead's my anode, copper has to be my cathode. That makes sense. My flow of electrons still has to go from anode to cathode. Still has to go from PB to Cu. I represented my arrows. That makes sense as well. Every voltaic cell is going to have a salt bridge. Every voltaic cell is going to have electrolytes. There's a voltmeter, probably a different measurement. But everything else is correct. That is a voltaic cell diagram for lead and copper. But you know me, didn't save mine appropriately. I don't know why. Let me scroll on down and see if I could just edit that quick. That is the example that we should have had from last time. So again, if it does that to you, I'm just going to cut it and paste it back in. Control X, Control V, click off it, and hopefully it allows me to save it. Doesn't like me today or ever. It's okay, because I like you guys. I'm here for you. And it did to me again. I'll have to edit this a little bit later. Does anybody have any questions on anything we did there for that example? Long example. Spent a lot of class time talking about that example. Any questions on that? It's a little bit wrong here, but I'll have to edit that. You should be able to do all that by now. Voltaic cells. All right, let's move on forward. Last 40 minutes of class. Here we go, 42 minutes of class. You could cross this all out. We're all done with voltaic cells. Last topic is going to be electrolytic cells, which we'll talk about next class. You can see that there's not a ton of information. It's like one full page of notes of topic 5. The last page of notes is like comparing and contrasting voltaic cells versus electrolytic cells. So that should be more of a review on topics 4 and topic 5. All right, so we don't need this open anymore unless you want to use it for the examples. The rest of the class, we're going through the examples on Unit 8, Topic 4, Voltaic cells. So please open up the examples, Unit 8, Topic 4, Voltaic cells. It's a Google Forms. We will do this one together. And then once we get done with this, I'll give you time to work on the exit pass on this topic as well. So again, I will leave my notes open just so I can refer to them. Maybe you want to attempt it without your notes open. It's okay, I'm not grading this assignment. I grade the exit passes. All right, here we go. Question number 1. Hopefully you have it opened. Unit 8, Topic 4, Voltaic cells. Question 1. In a chemical cell composed of 2 half cells, ions are allowed to flow 1 half cell to another by what? How do ions flow in a voltaic cell? I have 24 people on. I'll wait for at least 6 responses. Please put your answer in the chat once you have an answer. Question 1. In a chemical cell composed of 2 half cells, ions are allowed to flow 1 half cell to another by means of what? I have 5 responses so far. I need one more response. 1, 2. So 5 of you guys know what you're doing. One more, please. Thanks, Jumila. Thanks, Zen. Thanks, Tintin. Thanks, Faith. Thanks, Michael. Ions flow through the what? Please put the answer in the chat. Need one more so we get rolling. Thank you. Salt bridge. Ions flow through the salt bridge. Number 1, best answer is going to be choice D. 1 is D. Salt bridge, ions flow. Number 2, which type of reaction in a battery produces electrical energy? Which type of reaction in a battery produces electrical energy? 45 seconds. Think about it. Then we'll go through the answer. Give it a shot. Once you have your answer, please record in the chat. Still have 10 seconds here before I go over it. Okay, please record your answer in the chat. I have 4 responses. We're 4 for 4. Thank you. Thank you, ladies. Need 2 more responses, please. Thank you. Thanks, Alex. Battery produces electrical energy through which type of reaction below? Perfect. Thank you, John. This whole unit, we're talking about redox reactions, oxidation, reduction reactions, redox reactions. Batteries produce electrical energy through a redox reaction. 2, the best answer is going to be choice C. 2 is C. Next up, number 3. The redox reaction in a battery during discharge can best be described as what? So voltaic cell, discharge can best be described as what? Think about it. Give you 40 seconds for this one. Please record your answer in the chat once you have an answer. Okay, please record your answer in the chat for number 3. What's the best answer for number 3? Tough question. Thank you. Four answers so far. So this is definitely a tougher question right here because we didn't talk about electrolytic cell yet. So this right here, this part I'm highlighting is topic number 4, voltaic cells. Topic number 5 is going to refer to electrolytic cells. We didn't talk about that part yet. We didn't talk about non-spontaneous reactions. So first thing I want to figure out is a battery spontaneous or non-spontaneous? A voltaic cell, aka a battery, is spontaneous. What does that mean? It's going to happen automatically if you have all the right parts. All the right pieces there, the battery will operate. Non-spontaneous, you need extra energy for the reaction to occur. So we could have got rid of B. We could have said it's going to be either B or D. Because voltaic cell is spontaneous. Next up, let's check it out. Occurring in a chemical cell or occurring in electrolytic cell? Electrolytic cell, it's going to be, again, topic number 5. Electrolytic cell, we didn't get to that part yet. Occurring in a chemical cell. So choice B is going to be the best answer for number 3. Spontaneous and occurring in a chemical cell. 3, best answer is going to be choice B. Hopefully you followed along. Number 4, a battery consists of which type of cells? A battery is going to be a voltaic cell. What's the best answer for number 4? Let's give you a 30-second timer. Please try it out. Record your answer in the chat once you have an answer. Couple different responses. Sorry, I muted for a second. So first things first, we have a lot of B's. We have some A's for responses. Checking it out. A battery is going to be a voltaic cell. Battery is a voltaic cell. Think about voltaic cell. Voltaic cell, what does it say? Electrochemical cell in which spontaneously chemically reacts. Chemical reaction produces a flow of electrons. All right, there's actually electrochemical right there, electrochemical right there. Other things to note here, electrolytic cell, which we didn't talk about yet, is the same thing as electroplating. Electrolytic, electroplating, that's topic number 5. So that might have been a little bit of a curveball because we didn't talk about those yet. D, electromagnetic spectrum we talked about, but that is not going to be a choice for these cells. 4, the best answer is going to be choice B. 4 is B. 4 is B. Nice job on that one. Number 5, which kind of reaction occurs during an operation of nickel-cadmium battery? You have 2 different electrodes, a nickel and a cadmium electrodes. What's going to happen here? 35 seconds. Give it a shot. Please record your answer in the chat. Thanks, Faith. Yes, you're right. Yes, Tintin. Yes, Alex. Please record your answer in the chats. I have 3 responses, 4 responses. Yes, Nadina, thank you. Or nudge your brother, tell him wake up. Yes, Michael. Thank you. Spontaneous redox reaction. Thanks, Urban. Spontaneous redox reaction. What's that mean? A voltaic cell is going to happen automatically, and you have reduction, red, read, and you have oxidation. You have oxidation and reduction occurring in a redox reaction. Leo says Gur. 5, the best answer is A. 5 is A. Next up, diagram shown represents a chemical cell, voltaic cell. In order for the cell to operate, it should be provided with what? What is that voltaic cell? What is it missing? 20 seconds on the clock. You should be able to spot this pretty quickly. Please record your answer in the chat. What is that voltaic cell missing? There they go. We're rolling. That's what I like to see. A bunch of C's rolling in. Confident. You know this one. Label there for you. It's a salt bridge. It's missing. Hi, Yassine. How you doing? She got ya. Did she get ya? Thank you. Yeah, it's definitely missing a salt bridge. Salt bridge, choice C. Best answer. I just didn't want you to miss out on this party. Number 7, 2 more questions. Which process occurs in the operating electrochemical cell? Which process occurs in an operating electrochemical cell? Think about it. Use your notes if you need to. 35 seconds on the clock. Record your answer in the chat once you're done. Please record your answer in the chat for number 7. Produces means okay, number 7, here we go. Some answers coming in. A lot of D's, some C's. D is the best answer. Chemical reaction that produces. It's making electrical energy. So electrochemical cell, a voltaic cell is going to make that electrical current, that voltage. 7, the best answer is going to be D. Last question on the board. Here we go. It says, which statement is true for any electrochemical cell? Which statement is true for any electrochemical cell? 45 seconds. Think about it. Come up with an answer. Put it in the chat. Please record your answer in the chat for the last one right here. Use that corny phrase about red cat and an ox. A lot of correct answers here. Thank you very much for participating. We're talking about oxidation occurs at the anode, or reduction at the anode, or oxidation, anode, cathode. We're trying to figure out the location of the reduction and oxidation. What are you going to do? You're going to think of red cat and an ox, and this will give you that answer. So think about the process. Here we go. Oxidation occurs at the anode only. Anox, anode, the site of oxidation. That looks like it's a solid choice. Let's see. Reduction occurs at the anode. No, reduction occurs at the red cat. Reduction at the cathode. Definitely not B. Oxidation, choice C. Oxidation occurs at the anode and the cathode. No, oxidation's at the anode. Oxidation at the anode, not at both of them. Choice D, reduction occurs at the anode and the cathode. No, reduction occurs at the cathode. That's not true. Number 8, the best answer is going to be choice A. 8 is A. Again, the examples, you could submit them. You don't have to submit them. Oh, I missed one of them. Spontaneously. Choice B. Again, I do not grade the examples, but I do grade the exapasses. Hopefully, we got an 8 out of 8. That's the examples. Any questions on any of those example questions that we just went through? Thank you for participating for those who did. Okay, last thing for today's class, looking at the Google Stream page for a second, we went through everything but number 5, which is the exapass. So from here to the end of class, I'm going to give you a ton of time to complete this exapass on topic 4, voltaic cells. There's 7 multiple choice questions on voltaic cells. I'm going to ask that you complete these questions right now here in class from here to the end of class. Please open up the exapass, Unit 8, Topic 4, voltaic cells. And I'm going to put you in breakout groups by yourself. In the event you have any questions, feel free to ask for any help here. So again, 7 questions. If you pay attention to the notes, pay attention to the examples, the flicks, the demonstrations, you should be good to go for this exapass. This is graded. Please join your breakout room. Please complete this assignment here till the end of the period. If you finish it early, you're more than welcome to leave. So have a great day. Make good decisions. Get out there. Enjoy this weather. It's going to get a little cooler the next couple of days. So take advantage of a walk here or there. Maybe you want to focus on your chemistry for a while. But again, please work on this exapass from now to the end of class. If you have any questions, please ask for help. Please join your breakout room. Have a good day. We'll see you guys. Please join your breakout room. Please complete the exapass. Topic number 4, voltaic cells. Joey G, Jordan, please join the breakout room. Please complete the exapass. Once you're done, you're free to leave. Hey Kim, not sure how long you're gone for, but we wrapped up the rest of topic number 4, Voltaic cells. What's going on now? Right, people are working on the exit passes of topic 4. If you have questions, feel free to ask for help. But I did record the class, and I will post it up here so you could review anything you need to. Let me know if you have any questions. Hi, Jumila. Good morning.
Hi, Mr. Brown. I didn't have a question about the exit pass. I just wanted to know if when we finish, if you wanted us to leave or come back to the main room.
No, you're all set. You're free to go.
All right. Thank you.
You're welcome.
Have a
Have a
good
good
day.
day. You too. Thanks. All right, guys. Have a great day. Make your decisions. We'll see you later. Please do not forget to do the exit pass. Have a good one.